Hello everyone, this is Sir Aris. Today, let us talk about uh, further topics in Introduction to Complex Numbers. We'll be talking about Euler's formula, powers and roots of complex numbers, the exponential and trigonometric functions, and hyperbolic functions. The Euler's formula is known as the exponential of I theta equals cosine theta plus I sine theta. Using this formula, we have justified writing any complex number as, so our definition for complex number is z equals x plus iy, where x and y are real numbers. Uh, in terms of the magnitude r and the angle theta, x is r cosine theta, y is r sine theta. Factoring out r, we have r cosine theta plus I sine theta. This from Euler's formula is given by EI theta, so we can write z as r times e to the power of I theta. So for example, we find the values of um, 2ei pi over 6. So we can use directly this expression, or so for the first, there are four of them. EI pi and E2 and pi I are quite easy, so we'll skip them. We'll try this part, let's call it part A, 2e I pi over 6. We also do part C. Okay, this is written as r e I theta with r equals 2, and theta is equal to pi over 6. So if we look at the complex plane xy, oops, or xy complex plane, the angle pi over 6 is over here. So suppose this is a total length 2, and this angle is pi over 6. So this distance would be 2 times sine of pi over 6. So this is 2 times sine of pi over 6, or that's 2 times 1 half, or 1. While this one here is 2 times cosine of pi over 6, or square root of 3. So 2 to the power of ei pi over 6 can be written as uh, real part is square root of 3 and imaginary part 1. Okay, so part B is this, but that's easy. Pi being over here, so you simply have 1 or 0 on the x-axis, so it's simply I. This one is I. For um, this part, 3 times e to the minus I pi over 2. It's part C. E to the minus I pi over 2. Here, there's a 3 also. R is 3, while theta is minus pi over 2. It's actually not so difficult also. So if you look at the xy complex plane, um, with r equals 3 and minus pi over 2 is over here. So that's an angle minus pi over 2. So if this is 1, 2, 3, that would be your point 3e minus I pi over 2. Or that's with a real part 0 and imaginary part minus 3. So you have 3e to the minus I pi over 2 equals minus 3i. Okay, another example is, let's evaluate 1 plus I quantity squared divided by 1 minus I. So in the xy complex plane, so suppose this is 1, minus 1, 1, and minus 1. 1 plus I would be that point where real part is 1, imaginary part is also 1. So that's our 1 plus I. 1 minus I, real part 1, imaginary part is minus 1, so that's over here. So 1 minus I. This is our 1 plus I. This is our 1 minus I. So you know this is 1. So the length here is square root of 2. This one is also square root of 2. This one is pi over 4. This is minus pi over 4. Okay, so 1 plus I therefore can be written as square root of 2 e to the power of I pi over 4, whereas this 1 minus I is equal to square root of 2 e minus I pi over 4. So if you have 1 plus I squared divided by 1 minus I, that's square root of 2 e I pi over 4 squared divided by square root of 2e minus I pi over 4. And that would be square root of 2 squared divided by square root of 2, that's square root of 2. The numerator is e to the I pi over 2. And the denominator, you bring that on top, that's e I pi over 4. So I pi over 2, or 1 half, plus 1/4, that's 3/4. So this is square root of 2 e I 3 pi over 4. 3 pi over 4, so if this is pi over 4, this is 2 pi over 4, 3 pi over 4 is right here. Okay, so this whole thing is 3 pi over 4. And this is still square root of 2. You have 1 here and 1 here. So this point is simply um, minus 1 plus I. Or our 1 plus I squared divided by 1 minus I is negative 1 plus I. Okay. So next part, we uh, raise the complex number to the power n. So if you write in terms of magnitude and theta, you have the power of n. You can write that as Rn to the times e to the power of I n theta. So you have I theta for r equals 1. You have e I theta to the power of n, can be written as Euler's, using Euler's formula, cosine theta plus I sine theta n, or we put n inside e I n theta, that's equal to cosine n theta plus I sine n theta. So the nth root, if you raise z to the power of 1 over n, you have r e I theta 1 over n. So r 1 over n times e to the power of I theta over n, or nth root of square root of, or nth root of r times cosine of theta over n plus I sine theta over n. Example, we want to evaluate cosine pi over 10 plus I sine pi over 10 to the power of 25. So cosine of pi over 10, oops, plus I sine of pi over 10 to the power of 25. This inside the bracket is, it can be written as ei pi over 10 to the power of 25, or ei 25 pi divided by 10. And this can also be written as ei 25 divided by 10. You can write that as 5 pi divided by 2, or 5 pi divided by 2. That's ei 2 pi, and um, I pi over 2. And this also um, would further simplify to, this one is 1, and this one ei pi over 2 on a complex plane. That would be um, pi over 2 is here. That's your pi over 2. So with a magnitude of 1, this term is simply I. This one is 1, so 1 times I is I. Okay, another example. Find the cube roots of 8. Now, if you already know, if you take the square root, so this is just um, a review, that square root of 4 is um, 2 or minus 2. There are two roots, two square roots of 4. Um, if you do square root of 8, so now if you have square root of 8, the obvious answer is 2, but there are also two other roots which we are trying to solve. So to get this, it may not be too obvious, but we can write 8 in uh, in the general complex form, 8 ei theta, where here theta is, it could be 0, 2 pi, 4 pi, 6 pi, and so on. Or so here, if we take the cube root of 8, you have 8 ei theta to the power of 1 over 3. That would be, so cube root of 8, absolute value of 8, that would be 2. And e to the power of I theta over 3, where um, theta over 3 would be 0, 2 pi over 3, 4 pi over 3, 6 pi over 3, and so on. Or in terms of degrees, you have 0 degree, 120 degree, 240 degree, goes back to 360 degrees, and uh, so on. But after 360 degrees, that's just equal to 0. You just continue then adding up 120 degrees. So on the xy complex plane, if this is our point, so this is, suppose this is 1 and this is 2. Here, that's our point 2 and 0 degree. Here at this point, at 120 degrees from the x-axis, that is our 2 and 120 degrees. And here, that would be your 2 and 240 degrees. So this is at point is at a height of square root of 3. This one is minus square root of 3. And here this is 1. Okay, the length here is 1. So in the complex plane, we saw 3 points corresponding to the cube root of 8. So the cube root of 8 is therefore equal to a set containing 2 minus 1 plus I squared root of 3 minus 1 minus I squared root of 3, and that's it. Now let us consider exponential and trigonometric functions. Using Euler's formula, ei theta is cosine theta plus I sine theta. E to the minus I theta is cosine theta minus I sine theta. Now we add the two equations, so adding 2.8 and 2.9, and dividing by 2. So we add this 2, we get 2 cosine theta, divide by 2, so we can write cosine theta equals e to the power of I theta plus e to the power of minus I theta divided by 2. We can also subtract, so subtracting 2.9 from 2.8 and say divide by 2i. So you have sine theta equals, so we subtract I sine theta minus I sine theta, that's 2i sine theta. Cosine theta minus cosine theta, that's 0. So you have e I theta minus e minus I theta divided by 2i. Okay. Similarly, in the same manner, we can write for any complex number z, cosine of z equals eiz plus e minus iz divided by 2, and sine z equals eiz is e minus iz divided by 2i. Okay, this is sine. Okay, so we have these two equations. Example, find cosine I. So you want to find cosine I. Cosine I using our formula, this one. Cosine I is I, or z is I, plus e minus I divided by 2. So that's e to the power of minus 1 plus e to the power of 1 divided by 2, or that's 1 over e plus e divided by 2. If you use your calculator, it will be 1.543 and so on. Okay. Another example, evaluate sine pi over 2 plus I ln 2. So sine of pi over 2 plus I ln 2, that would be equal to e to the power of, sorry, definition of sine is over here, iz theta, iz minus e minus iz over 2I. So that's ei pi over 2 plus I ln 2 minus e minus I pi over 2 plus I ln 2 divided by 2I. That would then be e I pi over 2 times e I times I, that's negative 1, negative ln 2 minus e minus I pi over 2 times e minus I times I, that's 1 ln 2 over 2I. Simplifying ei pi over 2 in the complex plane, that is simply I. So you have e minus ln 2. And by the way, negative ln 2 is just ln of 1 half minus this one in the complex plane, x, y. This one is pi over 2. Here, that is our minus pi over 2. So that's minus, this one is minus I. It's e to the power of ln 2. The i's actually cancel. So you have e to the ln, or let's write it as e ln 1 half plus e ln 2 over 2. E to the power of ln 1 half is actually 1 half. E to the ln 2, that's 2. 1 half plus 2, that's 2.5, or 5 over 2 divided by 2, that's 5 over 4. So that's our value for sine pi over 2 plus I ln 2. Okay. So now let us consider for a purely imaginary number I, y. Then we can write cosine iy equals e to the power of iy, or I times iy, plus e to the minus I times iy divided by 2. And then this would simplify to e to the minus y plus e to the y divided by 2. On the other hand, if you have sine iy from our formula, you have e iy minus e minus iy divided by 2I. That would be um, e minus y minus e y over 2I. If we multiply both sides by I, or if we multiply the numerator and the denominator by I, you can get rid of the I in the denominator. So I times I is negative 1. So we can also exchange these two to get rid of the negative. You have I ey. So take note, I would rearrange this. So ey minus e minus y over 2. Okay, this I is outside the fraction. Now let us define functions that are equal to this inside the parenthesis and this here. Okay, or also we can set them equal to cosine of iy. So let's say cos z is equal to cosine of z if z is has an imaginary uh, term. Also, we define sinh of z as minus I sine of z. So in this case, from our formula, we have cos of z equals ez plus e minus c divided by 2, and sinh is sin h z equals e z minus e to the minus z divided by 2. These two are what we call the hyperbolic sine and cosine functions, or hyperbolic cosine and sine functions. So you can read it as cos or sinh, but technically you can just say hyperbolic cosine for cosine h and hyperbolic sine for sine h.